So why is the ocean blue? And more importantly, why are you probably wrong about it? Yeah, you heard me. We call Earth the blue planet, obviously, but the reason why it's blue? Well, let's just say that little fact you learned in 3rd grade, it's time for an upgrade.
Come on, let's be honest with each other for a second. You think it's reflecting the sky, don't you? It's okay, you can admit it. The big blue ocean is just a giant mirror for the big blue sky. It's neat. It's simple. It makes a certain kind of sense. And it's also completely wrong.
Hey, no judgment here. Seriously. For the longest time, that was the scientific explanation. But, science does this thing where it progresses. So it's time you did too. Let's get you caught up.
All right, first order of business, we've got to tear down this whole sky-high misconception. Let's just get it out of the way so we can move on to the cool stuff.
So here's the showdown. In one corner, you've got the convenient lie, sky reflection. Simple, easy to remember. In the other corner, you have the weird truth, molecular vibrations. Yeah, it sounds a little more sciencey, but trust me, the truth is so much more interesting.
So this whole idea started getting shaky way back in 1921. You've got this physicist, C.V. Raman, on a ship, and he looks down at the water and just gets a feeling. He's like, nah, that can't be right. So with just the gear he had on board, he starts doing some experiments. And what he found was that the blue color wasn't being borrowed from the sky at all. It was an inside job. The color was coming from the water.
And really, here's the nail in the coffin. Think about it. What happens on a cloudy day? The sky is gray, right? So if the ocean was just a big mirror, it should be gray too. But it's not. It's still blue. Maybe a darker, more dramatic blue, but it is definitely 100% blue. Checkmate.
Okay, so if it's not reflecting the sky, then what in the world is going on? Well, the real story starts with sunlight. And it turns out, water molecules are incredibly picky eaters.
See that light coming from the sun? We call it white light, but it's not really white at all. It's actually a big jumble of every color of the rainbow all smashed together. Think of it like a party bus of colors heading for the ocean. So step 1, this whole rainbow of sunlight smacks into the water. Step 2, the water molecules get to eating, and they love the long wavelength colors. They just gobble up the reds, the oranges, the yellows. But, and this is the important part, they're not so hungry for the shorter wavelengths, like blue. So, step 3, the leftover blue light doesn't get eaten. It gets to dive deeper, bounce around, and eventually gets scattered right back out, into your eyeballs. Okay, I know what you're thinking. Wait a minute. If water is blue, why is the glass of water on my desk totally clear? It's a fair question. What gives? The answer is volume. Look at this picture. The water in that bucket is the exact same water that's in the pool. But the bucket water is clear and the pool water is blue. Why? Because the blue effect is really, really faint. You need a ton of water molecules all working together to absorb enough red light for you to actually see the blue that's left over. It's a team effort. All right, so we've established that water absorbs red light. But why red light specifically? To get that answer, we need to go deeper. And I mean like molecularly deep. This is where it gets really weird and really, really specific. This right here, this is what makes water a total freak of nature, in the best way. See, pretty much every other color you see, green leaves, a red car, whatever, that color comes from electrons inside the atoms getting excited and absorbing light. But not water. Oh no, water is different. Its color comes from the vibrations of the molecule itself. Picture an H2O molecule. It's having its own little private dance party. The bonds connecting the hydrogen and oxygen atoms are constantly stretching and bending. It turns out the exact amount of energy needed to get those bonds really jiggling and stretching just so happens to be the exact energy of red light. So when red light shows up, the water molecule basically grabs it and uses that energy to power its dance moves. Seriously, think about that. As far as we know, it is the only molecule in the entire universe that gets its color this way. It literally vibrates a color. That is just wild. And if you need the ultimate proof, the smoking gun, here it is. On this graph, you see regular H2O compared to something called heavy water, or D2O. The only difference is that the hydrogen atoms are a bit heavier. Because they're heavier, they vibrate slower. And that slower vibration absorbs light that's outside our visible spectrum. The result? Heavy water is completely colorless no matter how much of it you have. That proves it. The blue color is tied directly to the unique dance of the H2O molecule. Okay, so pure water is blue. Case closed, right? Well, not quite. Because just blue would be way too simple for Mother Nature. The ocean is rarely pure H2O. It's more like a giant, messy soup full of other stuff.
You see greenish water? That's probably thanks to a bunch of microscopic algae called phytoplankton. Murky, brownish water? That's just mud and sediment kicked up from the bottom or washed in from rivers. And that gorgeous turquoise you see in vacation photos? That's the blue of the water combined with bright white sand on a shallow seafloor. And this basically answers the question of why rivers in most lakes aren't blue. For one, they're usually too shallow. But more importantly, they are just chock full of sediment and organic gunk. All that stuff messes with the light and completely overpowers the water's natural intrinsic blue.
All right, let's go on one last little journey straight down. Because as you go deeper, another factor comes into play: depth. The more water light has to punch through, the more it gets filtered. As we descend, colors start to disappear, one by one. Just 5 meters down, pretty much all the red light is gone. Go down to 25 meters and say goodbye to orange and yellow. By 60 meters, even the green light starts to fade out. At 200 meters, you're in what they call the twilight zone, where only a little bit of blue light can reach. And then at 1,000 meters, you're in the midnight zone. It is absolute total blackness.
First to get knocked out, goodbye red.
Then, a little deeper, so long yellow.
Deeper still, good night green.
And finally, hello, darkness. Down here, in the deep, the sun is just a memory. The only light you'll find is the kind that life makes for itself. It's called bioluminescence. Creatures making their own ghostly light to find food, find a mate, or just scare off predators. It's a private light show in a world of absolute darkness.
So there you have it. You are now officially an expert on why the ocean is blue. I expect you to go forth and correct people at parties. Use your new power wisely. Look, if you're going to remember just one thing from all this, make it this. The ocean is blue because H2O molecules are just a bunch of high-energy weirdos that absolutely hate red light. They absorb it, and the blue is what's left over. The end. Which really makes you think, huh? If you've been wrong your entire life about something as simple as the color of the water, what else have you been wrong about?